Hello. So we learned what is a best estimator in the previous videos. But as I said at the end of the last video, we'd like to extend our framework. So let's think about this problem, pregnancy due date. So due date is another estimation problem, given doctors estimate when the baby arrives. Okay, so back when my wife was pregnant, her due date was February 15th. But so this is an estimator, but still it is incomplete. I want more information, and also I know that that estimator is likely to be wrong. By the way, recently I went to a baby shower, and there was a quiz. How many percentage of babies arrive on their due date? The answer was 5%. So the due date is correct only for 5%, right? So 95% it is wrong. And everyone knows that it cannot be correct. So anyhow, then it does not answer some important questions like until when can she work? And can I have a schedule on February 10th, 5 days before the due date, right? For example, when so the due date itself does not answer that question, right? So then, how can we improve the estimation? A better way would be giving an interval, right? So the baby will arrive sometime between February 5th and February 25th. So if you give me an interval, then I can do something I can extract more information. For example, okay, so the baby may arrive on February 10th, so I'm not going to make any schedule at the time, for example. Or she can, start on leave, her leave from February 5th, for example. So then, statistically, we are extending the point estimation to an interval estimation. Literally, point estimation is estimating a parameter, which is a point, using a point, right? Parameter is a number, and we are estimating the parameter using a number. And it is simple, intuitive, and that's what we learned up to the last video. But the problem is, as I said, it does not say anything about its accuracy, right? So, due date is February 15th is important information, but does not say how much do I have to rely on this, right? Instead, interval estimation is estimating one point using an interval, right? So it provides information about the accuracy. If you are confident about your estimation, your interval can be smaller, right? But if you are not that confident in your estimation and you may think, there will be large errors, then you need to extend, you need to give a larger interval, or larger margin of the error. Okay, that is what we are going to study here. So suppose that, here in this video, I will fix the point estimator first. So we are estimating a parameter, theta, and we have a good point estimator, theta hat. So for example, when you estimate population expectation, we know that X bar, the sample average, is the best point estimator. So we take that as granted. From there, what we are going to do is we are going to allow some margin for errors around the point estimator and make it an interval like this. So M is the margin for errors, and you subtract and add the margin around the point estimator. That is an interval, right? So then you may interpret it this way. When I say this is my interval estimator, then I'm saying that, okay, the true parameter will be in between these 2 points on this interval, right? And we say theta plus m is the upper confidence limit, and say theta minus m is lower confidence limit, and the interval itself is called confidence interval. I am confident that the true parameter will be in between these 2 points. So we say it is the confidence interval. Okay? And the structure is pretty straightforward. And the confidence interval is said to be correctly estimating the parameter as long as the true parameter is between those 2 points. Right? Obvious, right? And of course, it may be wrong by random errors. So the error probability is usually denoted as alpha, and that is when the true parameter is outside of this interval, right? So either the true parameter is smaller than the lower confidence limit, or if the true parameter is greater than the upper confidence limit, right? So outside probability is error, right? If the true parameter is outside the interval, that is error. And in other words, if alpha is the error probability, then 1 minus alpha is the probability that your interval is correct. So you can use 1 minus alpha for the probability that the true parameter theta lies between the lower confidence limit and the upper confidence limit. That probability, so the probability that your interval contains the true parameter, is the correct probability of correct estimation, and we call that the confidence level. How confident you are. So if that probability is higher, then you will be more confident. So we say it is confidence level. So all the names are confidence here: confidence interval, confidence limit, confidence level. So then, okay, so far it is pretty intuitive. And we are going to think about 2 intervals. First, say about the due date thing. So first, suppose that, say, there are 2 doctors, and a doctor tells us the baby will be born sometime between February 5th to February 25th. And suppose that there was another doctor who told us the baby will arrive sometime between January and March, right? Which is more informative? So, in this case, so say the baby will arrive sometime between, like, in January or February or March. Actually, this statement does not contain any information. Even anyone who is not a medical doctor can say that. It is kind of obvious statement. So in that sense, it is not informative. I would say estimator 1 is more informative. So I will take A. But what do you think about this? Which has the higher confidence level? So think about 2 estimators. Remember, the confidence level is the probability that your interval estimator correctly contain the true parameter. Which one would have a higher confidence level? The answer is B, right? So even if it's obvious, so when I say obvious, that means it always happens. It is always true. So that's the definition of obviousness, right? So it is obvious that the baby will arrive like in January or February or March. So it is nearly 100%, like 99.99% correct, right? Unless there is any problem, complications, it will be true. But the first estimator may be wrong, right? So it is possible that the baby arrives on February 4th or February 26th. Still, this estimator is wrong. So in that sense, estimator 2 is more likely to be correct. So it has the higher confidence level, right? So what I wanted to show you here is that earlier I said estimator 1 is more informative. So estimator 1 is good in that sense, but that doesn't mean it has a higher confidence level. So of course, the higher the confidence level, the better, but it is not always better. There is a trade-off, right? So when you compare these two, you can like think like this. The margin of error is smaller for estimator 1. So it is more informative. You can have a better idea. Oh, it'll be around here and on this smaller set. So it's more informative. But the problem is the smaller the margin of the error, the more likely to be wrong, right? On the other hand, so if you want a better probability of, or minimize, if you want to minimize the error probability, you can simply extend the margin of error. Then, in the end, you will have 100% confidence level. But the problem is there is no information. So anything is possible, then you are never wrong, but no information contained. Okay, that is a trade-off. So you have to understand that when you use an interval as an estimator, there are two different criteria. First, you would like to have the smaller margin. The smaller margin, the more informative, right? At the same time, you would like to have higher confidence level, because that is probability of correct estimation. So the higher confidence level would be good, given everything else being the same, right? But as I said, this is trade-off. Extending margin of error. So to have higher confidence level, you need to extend the margin of error, but that will make your estimator less informative. So we have to balance this trade-off. How can we do that? Our idea is to fix one of these two and optimize the other thing. Usually in practice, we are going to fix this confidence level. Fix the confidence level first and then minimize margin of error as long as the confidence level is satisfied. Okay, so that is what we usually do in practice. For example, usually we think of 90%, 95%, 99%. Like each of them imply, say, 10% error probability, 5% error probability, 1% error probability. So error probabilities are allowed at a certain level. So it's your choice. How much you are willing to accept, how much you are willing to allow the error to happen. And then, depending on that, I would like to make a most informative interval estimator, or I'd like to make the smallest margin of error, right? Among these three common choices, like 95% is maybe the most common choice. So the standard is 95%, but depending on the cases, you may either choose 90 or 99%. They are also not that uncommon, like they are also used in many places. So then, now think about this. If you understand the trade-off, you can expect which confidence level would yield the widest confidence interval. The widest one. Okay, so the answer is 99%. So when you widen your confidence interval, then it is more likely to contain the true parameter because it's wider. So your confidence level will be higher. So 99% should have the widest confidence interval, right? So that is the trade-off. Now, okay, we defined margin of error, the confidence interval, and we learned basic terms like error probability, confidence level, margin of error, and the trade-off between margin of error, the size of margin of error versus confidence level. And what remains is, how can we calculate the margin of error? So, as I said, we are going to fix the confidence level, and then we minimize the margin of error. We are going to derive the formula from now on. Especially, we are thinking of the case where we are estimating the population mean. So, when you estimate the population mean, we start from the best estimator, which is the sample average. So there is no doubt simply we know the point estimator should be the sample average. Okay, sample average can be entered here. Theta hat is the x bar sample average, right? Then what remains is to derive the marginal error. So if you can calculate the marginal error, then you have an interval. How can you do that? This is our idea. Okay, again, we need to satisfy this equality. The probability that your interval contains the true parameter mu, right? Population mean should be 95%. So this is the clue, and from here you are going to calculate m. Think about this. Mu is the population parameter, which is unknown. We don't know, we are guessing about this, so we cannot utilize it. And x bar is random variable, so probability is related to this, associated with this random variable. And we know x bar is approximately normal distribution from the central limit theorem, right? So then m is the unknown in this equation. In this equality, mu is unknown but fixed, and what we want to solve for is m. X bar is random variable, following a normal distribution. So that is our basic plan how to calculate m, right? So first step we are going to do is, because this randomness is coming from x bar, we are going to use normal distribution for x bar. We will rearrange these terms so that x bar is in the middle. Okay, so subtract x bar from all three terms, and also subtract mu on three terms, then you have this, right? So these two inequalities equivalent to these two inequalities. From there, we are going to use standardization of the normal distribution, blah, blah, blah. So in the end, we are going to obtain m, the marginal error. So I'm going to do that in the next video. Next video will be derivation of the marginal error, utilizing the results we learned from chapter 6 and 7. Okay, thank you for watching. I will stop here and continue in the next video.